Okay, so as we go down the periodic table and we look at the ions, the fluorine ion, fluoride ion, the chloride ion, the bromide ion, the iodine ion, as it increases in size, what do we expect about the basicity? Do we expect it to increase or decrease? Okay, so it's gonna increase. Okay, so if we have it in an aprotic solution, so do we expect these ions to cause it to increase or decrease in terms of its nucleophilicity? Mm-hmm. Okay, and if it's in a protic polar solution, it decreases as size increases or decreases. So I mean, so as size increases, it becomes a better, it becomes a better nucleophilic compound, right? Because it's getting bigger, so it's going to be easier to get those electrons moving, right? Where in a polar solution, where in a aprotic polar solution, then in that case it's going to be just the opposite, right? So it's going to be not as, willing. That's right. And we know that, let's say, the iodide ion is a better nucleophile or a stronger base than fluoride, right? Yeah, no, maybe. And do you guys remember why that's the case? Iodine is bigger. That's right. You're not taking my electrons. That's right. Okay. Okay, so this is just basically showing us why. And again, I apologize for you guys not being able to see the top. Yeah, it is what it is. Okay, so so if we take a look, and here's our fluoride, and then here's our iodide, right? And so our fluoride is going to be pulling everything kind of real tight. Okay, so then in this case, we're going to have a strong ion dipole interaction, where here we're still going to have an ion dipole interaction, but it's going to be much weaker because the iodine is so big compared to it. It's what is it called? The nuclear effectiveness is going to be significantly less compared to that of the fluoride. And so, in other words, those positive charges from the nucleus are going to be pulling more so on this case than it is on this case. Okay, so strong bases are going to form okay, so under aprotic conditions, they're going to behave opposite. Fluoride is going to be a better nucleophile. Under protic conditions, iodide is going to be a better nucleophile. And so before any of this can happen, before it could actually give up its electrons, it first has to disrupt those interactions, right? And so it's going to be easier to disrupt those interactions in this case, compared to in this case. And so again, that the the nuclear effectiveness of fluorine, since it's going to be so small, it's going to be pulling those things tighter, so making it harder to disrupt. So that's right. It's because you don't have hydrogen that's going to be causing the hydrogen bonding, and so which is a much stronger interaction than, let's say, just dipole. Okay, so hello. So here's an example of two aprotic polar solvents. So DMF, which stands for N-dimethyl formaldehyde, and then DMSO. DMSO stands for dimethyl sulfoxide. Okay, this is the structure. This is your dimethyl sulfoxide, and this is your DMF. DMF. Okay, and so you guys see that there's no oxygen with a hydrogen attached to it on both of those structures. Instead, we have the double bond. So the double bond is going to have it's going to get the partial negative charge, and then the carbon is going to get that partial positive charge. In this case, the oxygen is going to get the partial negative charge, and then also the sulfur is going to get the partial positive charge. And the interesting thing is that in this case, the methyl groups are going to kind of interfere with nitrogen being able to have any effect on it as well. So these guys are going to be able to solvenate a cation better than they're going to be able to solvenate an anion. Okay, because they don't, in the case of the cation, you're going to be using those partial negative charges, and they're going to be more accessible in this case than an anion, which would be able to have access here. So we're going to have less accessibility at these points than we'll have there. So again, if we think about it, so steric hindrance is going to play a part in that solute, the solute. Okay, does that make sense? Okay, so steric hindrance is going to basically decrease the nucleophilicity of compounds. Okay, so if we take a look at this here is ethyl oxide, and then this is tert but oxide ions. Okay, so this case is going to be a better. The oxide is going to be a better nucleophile than the tert because of the steric hindrance. So these guys are kind of surrounded by those methyl groups, so it's going to be kind of hard for it to interact. So you're not going to have access, easy access to other components. Where here, so here you're going to have easy access. Here, you're not going to have easy access because you have methyl groups that are going to be kind of interfering with things. Okay, so then the bute is going to be a stronger base than the ethoxide, but it's going to be a poor nucleophile. Okay. So, and you guys know that because in the case of the nucleophile, it's going to be harder for it to hit that backside, you know. So it's going to be, if the bigger it is, it's going to be harder for it to go to the backside, right? Where in the case of something that's smaller, it's going to be able to get into the backside. In an Sn2 reaction. Okay. So Sn2 reactions can basically be made up of a variety of compounds. Here. Okay, so here we have the formation of an alcohol when we have a terminal halide and a hydroxyl group reacting, or a primary. In the case of when we have an oxide or carboxide reacting with the primary halide, then you're going to get the formation of an ether. If you have the primary halide reacting with hydrogen sulfide ion, then you're going to get a thio group. If you have a terminal or a primary halide reacting with a carbo thio, then you're going to get a thioether. And then if you have it reacting with ammonia, you're going to get the primary ammonium ion. And then in the case of a tertiary amine, you're going to get a quaternary ammonium ion. And in the case of cyanide, the cyanide ion, you're going to get a nitrile. And then in the case of an alkyl, an Alkene ion, anion, then you're going to get an alkene. I'm sorry, an alkyne. And in all of those cases, you're going to end up with the formation of those ions as well. Okay, so all of these reactions are going to end up being irreversible, meaning that there's not going to be equilibrium associated with it. It's going to go one direction. And that's because the weak base can't be displaced by a strong base. So. Okay, so in the case of these Sn2s, we're going to get, it's going to be a single direction in this case. So you're not going to have the ability of going back the other direction. Okay. So in the case of the synthesis of an amine, so here we have a primary amine. The electrons are going to be donated from the amine, the nitrogen, to our acyl halide. Then those electrons, then are going to affect the bond, and then they're going to allow the dissociation of the ion itself. So we're going to end up with the formation of the intermediate, where this guy becomes plus. We still have that minus interacting, and then we have the bonding of in this case, the methyl group or the hydrocarbon. And you guys want to always kind of remember this. This is just represented, should be represented as R, because this is it could be any carbon chain, right? And then, especially if it's a primary, a halide rather than a tertiary, because it's easier for it to do that. Okay, so this intermediate forms, and then in the presence of potassium carbonate, it's going to end up making the solution a lot more basic. And so in this case, you're going to be pushing the reaction, and then you're going to get the formation of your amine, right? And then you're going to also have in excess amounts of your halide. You're going to have the second electron, lone pair electrons, to sit there and interact on the backside of this guy, and then this is going to allow for the dissociation of the iodide ion. And then, so then you'll get the iodide ion interacting weakly. You'll have a plus charge on your amine. And then with more KOH, you're going to get this guy going to the same thing. And then you're going to end up with a quaternary ammonium iodide. But then that has to take place in a basic solution. So in the case of a basic solution, then it's going to drive the formation of the quaternary ammonium iodide. Okay, so in this case, this guy is going to be a plus charge, this is going to be a minus charge, and this is going to be interacting ionically, right? And that's going to be in all of these cases, you're getting the dissociation, so that ion is just going to be able to interact. Okay, questions? Concerns? Cash? Okay, so let's test out our theory here, since we had a reaction. Let's say we have, let's do this. Okay, and that's going to be reacting with in the presence of CO3. Okay, what should be the product? guys are killing me right now. Okay, you have an answer? And then I want you guys to talk about the kinetics. Is it going to be a slow reaction, fast reaction, or neither? This guy was in the S formation. What would be the product? Would the product be no, it really can't be. Not the nitrogen, but can't be. Okay. Oh, actually, thank you. Okay, do we have an answer? Or structure? Okay. Okay. Carbon chain, one attached to the nitrogen. Well, there's an ethyl here. Okay. And then what else is going to be attached? For the iodine, I have 1, 2, 3. Yes. Okay, you will have two purple attachments. Where are they going to be located at? I know they're going to be attached to the end, but are they going to be? They're going to be like this. What's that? Because similar to this, right? Only thing we're starting off at this point right here, right? Okay, so in this case, we have the potassium, the potassium, or the electrons here being transferred over to here. It's going to disrupt this, and then this is going to be freed, right? This guy's going to have a plus charge on it. It's going to attach to, in this case, our propyl, our propyl halide. The iodide is going to be released from that that halide, and then we're going to have our very first attachment. The question is it going to attach backside or front side? Right, because if we take a look at this guy, right, so we have our very first attachment occurring, and it's here, and then attaches directly across, right? So in that sense, it's still going to be backsided, right? Carbon. And then here, are we attaching backside? Are we attaching the backside of the nitrogen, or are we attaching somewhere else? And you guys know what's happening in this case, right? What's happening in this case here? So which side do we attack from in those cases? From the back, right? So we're assuming that we're attacking from the back in all situations, right? So if we're attacking from the back, that's going to change our orientation, right? Is that true? So like in this case, it isn't going to matter because you have the hydrogen and the hydrogen, right? So you get attached from the backside of this hydrogen to cause this hydrogen to end up being, sorry, screwing up here. This guy is going to be attacking from the backside of this structure, right? The carbon. Backside. So it's going to be attaching on the carbon here. So in this case, we're not looking at the nitrogen, right? We're looking at where the carbon is, right? Because it's the carbon that's being attacked, right? So in this case, the nitrogen is donating its electrons at that point, and it's called the backside. In this case, the backside doesn't matter because they're all hydrogens, right? Because you have carbon, hydrogen, hydrogen. In this case, is it going to matter if we're attacking the backside? Because which carbon is being attacked? Is it going to be this carbon, or this carbon? So it's going to be one that's closest to iodine. 1, 2, 3, right? So this carbon here is going to be attacked in this case, right? And it's going to be, this is going to be attached on the backside. That. Still going to be attacking from the backside, yes. Okay, so then we get the formation of our intermediate, which is going to be this guy here. Okay, so us adding the base is going to do what? What did you do in these circumstances when we added the base here? What was that? No, actually, we removed that one hydrogen. Because we're starting out with just a single hydrogen. By us going through this very first reaction, we're removing that one single hydrogen. So the base is going to donate its electrons to allow for the charge to become neutral again, right? So then we'll get the formation of N. One, two, three. 1, 2, 1, 2, 3. Okay. So we'll get the formation of this, right? And then if we, with the excess base, or the excess propyl iodide, then what are we going to end up with? It's going to be so, because remember, we have more of this around, so we still have. That's right, again, right? Yep. Okay, so then we'll end up with our tertiary amine iodide. Two, 4. Okay. It's a ionic interaction. Okay. Everybody got it down? Can you guys see it? Can you reproduce it? You're supposed to say yes, you can reproduce it. Yeah. Okay. Clear. Okay, so here we have this tertiary alkali halide, and And then we also have water, which we know is a poor nucleophile, right? So in this case, we're actually going to get our alcohol, so our ternary alcohol, and then we're going to get the hydrogen bromide. Okay, so the thing is that this reaction actually occurs for one thing, right? And then it happens pretty fast. So the mechanism that we've learned before can't be the mechanism because we know that that tertiary amine is, the tertiary alkaline halide is going to be a slow reacting molecule. And then also we have a poor nucleophile, right? So for it to have a faster rate, something else has to be going on, right? Yeah. That one's gonna, the one right before here, that would have been a slow reaction, right? And again, that would have been a slow reaction because you had that chain being a little bit longer, but although, I should say, not too slow because it's still a primary amine, primary halide, right? So you still have the halide at the very end. It's not being buffered by a lot of things. So that makes it easier for that attachment to attach. But you have these chains that are going to act as steric hindrance because that nitrogen needs to be able to get to the point where it can donate its electrons, right? It's going to be it's still going to be a slow because of that nitrogen. But I'm saying that normally you would assume that it's going to be a fast reaction because you have, let's go back. The one that we have is a little bit different than the one that we've shown, but it's the concept is kind of the same. So, so this first step here, right? That one's going to be really fast, right? And then the next step is going to be slower, and then the next step is going to be slower. Why are each steps getting slower? And then not only that, in our case, we use those big carbons, right? Which adds more steric hindrance. It's harder for it to get itself in there. It needs to be able to get in there to react, right? So it's kind of like you get a really big person and they're trying to get through a little door, right? So they have to kind of maneuver to be able to get themselves through. So, or like a couch. Have you guys ever tried to move new furniture out of a regular sized door and you have to flip it in the right position? Exactly. Yeah, it doesn't matter either way because again, if the one that's attacked, he still has to get in there, right? And if he has so much stuff around him and where the nitrogen is located, nitrogen is going to be center. And at this point, we've added on, we're at this point where we have it basically surrounded. So these electrons need to get to the point where they can be donated, right? And so they need to be maneuvered in a way that they can get in. That orientation is necessary. Does that make sense? This is the thing that makes organic chemistry crazy because you have to think about, okay, so can I fit into that spot or, you know, so the rate is going to be dependent on only the concentration of the alkaline halide. Okay, so if it's only dependent on the concentration of the alkaline halide, so then it's going to be considered an Sn1 reaction, right? So it's not going to be dependent on both molecules. It's only going to be dependent on one molecule. Okay. So this is going to be an Sn1 reaction. So in this case, the solvent is going to be also acting as our nucleophile. Okay, so here we're adding on the ester group, or we're making an ester, right? Okay, and so these are going to be your products. You're going to get CH3O plus H2 and your bromine. So in most of the Sn1 reactions, the solvolysis reaction, or that basically means that the solvent is going to be acting as our nucleophile. Sn1, it's always going to be, or most cases is going to be where our solvent is going to be doing the job for us. Okay, so in the case of water, that's going to be exactly what happens. It's going to go through that process. So mechanism. So in this mechanism, what we're getting the carbon and the bromine bond being broken. And so in this process, it's going to be a slow process for this to happen. And then we're going to be able to get water to come in and act as the nucleophile. And water attaching to the carbon cation is going to be a fast process. And so then another water molecule is going to come and then donate its electrons to the hydrogen. The bond between the hydrogen and the OH are going to be broken. And then we're going to get basically the hydroxide, the hydroxide being added on to the ternary carbon, or that center carbon. And then we're going to end up with hydronium ion as a byproduct. Okay, so yes. So you always assume that unless it says equal parts, right? Then you assume excess, right? So if they just have it, particularly if they have it just written out as just H2O added on top, so then you just assume that you have tons of it. Coming from, yeah. And so, and that's the thing of also that you'll notice about OChem. They're never truly balanced in the equation. It's kind of understood that they're balanced, but a lot of times we add so much excess that we cause other things to happen, right? So if we use equal parts of it, right, then we know that we would only get that very first reaction. We'd get this, which is unstable, and then it would end up making either a double bond or it ended up making a double bond here, which would make it a ketone, or it would make an alcohol. But much slower. Okay, so in this case, these two parts of the reactions are going to be fast. The slow part is always going to be the formation of the carbocation. That's always going to be the slow part. Okay. Okay, and this is just basically showing us that, right? So here's our alkaline halide. This here is the free energy. So that's our rate limiting step. This formation of the carbon cation, it takes a lot of energy to sit there and make that happen. So that's going to be the slowest part of the reaction. And then once that happens, once we get to the cation, these are all downhill, right? So then they're going to be pretty fast. And so it's important to recognize that we have the water actually bonding to the cation ion, then causing that oxygen to have that plus charge. And then you also need water to get to the next step. Okay, so if we have a primary alkaline halide, it undergoes Sn2. If we have a secondary alkaline halide, it undergoes Sn2. If we have a tertiary alkaline halide, it undergoes only Sn1. Okay. So at the end of the day, the outcome ends up being the same, right? So you end up with that OH being attached to, and if we had water acting on these, but these, it's just the location of where it is. And it's just the rates are going to be different, right? And it's also going to be dependent on the concentration of the alkaline halide only. It's not going to be dependent on both molecules. The rate is, that is. And you guys remember rate reactions, right? K. Talking about it in 1D right now, so. Equals K, where K represents the rate constant times, in this case, we're talking about the alkaline halide. Okay, so Sn1, this is the case. Sn2, the rate is going to be dependent on what? So makes it it's going to be dependent on okay, so it's going to be the alkaline, the concentration of the alkaline halide, and what? That's right. That was the only thing that's left, right? So I'm misspelling it like crazy. Okay, so that's what makes it an Sn2 reactions, dependent on both, where this one is only dependent on one. So that's why I said Sn1. Okay, questions, concerns, relate? Okay. Okay, so in the case that we have, in the case that we have asymmetric center, and we have an Sn1 reaction occurring, so we're going to get both products, right? Both enantiomers. Okay, so we're going to get the one that's going to be going from the backside, and we're going to get the one that's going to be going from the other side. So then we're going to get the S and the R, or the yes. So yeah. So R represents one hydrocarbon. R prime represents a different hydrocarbon. R double prime represents a different hydrocarbon. So there's three different hydrocarbons. So they could all be the same or they could all be different, right? And so, but if the only way that it would be an asymmetric center is if they were three different hydrocarbons, right? So we know that under these circumstances, Sn1 reactions are going to give us both enantiomers. Okay. Okay, so why do we get a pair of enantiomers? Okay, so let's make it easier to see. So I'm going to call this X, Y, and Z. Okay, so when we get so we start at here, X, Y, and Z. Okay. So the first thing that happens is that we remember we get the formation of the carbocation ion, and then that's the first thing that's going to happen. Okay, and we get the bromine in this case breaking off, or the halide coming off of it. So that's our intermediate. So that's going to take the longest part, right? That's the slowest part of the reaction, this part right here. Then water is going to be able to come in and it can attach on this side of the carbon. So this is X, this is Y, and this is Z. Right? So it has the ability of coming in and attaching between the Z and the Y, or it can come in and attach between the X and the Z. Okay, so if it attaches between the Z and the Y, we're going to get this enantiomer. If it attaches between the Z and the X, the X and the Z, we're going to get this enantiomer, right? Same product, right? But different orientations, different terms. Okay. Okay, so then okay, so most Sn1 reactions are going to lead to a partial racemerization. So again, we're able to attack on both sides, right? So if the bromine is able to diffuse away, we can get attacking on both sides. If the bromine isn't able to diffuse away, then this guy's going to be blocked, and then we're going to end up attacking on one side or the other, right? Because you have the bromine kind of blocking that. Okay, so in general, the inverted product is going to form because, again, backside, easier to get to. And the front side is where the bromine's coming off. And so it's kind of blocking that area. Right? Okay. So this is just a summary of the experimental evidence for a Sn1 reaction. So the rate of reaction is only dependent on the concentration of the alkaline halide. That was the reason. So tertiary alkaline halides, but not primary or secondary alkaline halides, undergo Sn1. And then if the halide is attached to an asymmetric center, you'll produce a pair of enantiomers. And which one is going to be favored? Which enantiomer? Inverted or the and why? Yeah, it's blocked. Yep. It's often blocked. Okay, so the case of our Sn1 reactions. So these are going to be the relative reactivity of the alkaline halides in an Sn1 reaction. So the most reactive, again, is going to be Ri, then Rb, then Rc, then Rf. Right? Rf is going to be least reactive. Okay, so general trend, both was the case that we saw with the Sn2, right? So, consistent. The bigger you are, the easier it is for you to react. You're going to be a lot more reactive. Okay, so for comparing Sn1 to Sn2, Sn2 is going to be a one-step mechanism. Sn1 is going to be a two-step mechanism. The first step is going to give us that intermediate, that carbon cation intermediate. That's going to be the slow step, and then the fast steps are going to follow. Sn2 is going to be bimolecular rate determining step. And then Sn1 is going to be unimolecular rate determining step. So the rate is going to decrease with increasing steric hindrance. The rate is going to decrease with increasing stability of the carbocation. Maybe. Do this the old-fashioned way. That's right. But if this guy is stable, right, the longer the stability is, that means this part gets drawn out further, right? And so that means it takes longer to get to the next step because it's okay with being in that position, right? Where here, if it isn't stable, it's going to try to drive through this position to get to the next part. That's right. You know, it's kind of like Okay, so give you another example. So a lot of my students will, well, there are certain students that will start the sci-tech program at the same time that they're taking Chem2A, right? Because Chem2A, they're trying to become a nurse and everything like that. And they'll start the sci-tech program. The sci-tech program takes a year and a half to complete if everything's running smoothly. So they'll start making money. They'll start making 50K or something like that as soon as they graduate, right? And they get their job. 50K going in. And so we end up losing a good percentage of those students because they become comfortable, right? They become stable, making that money. And so they're like, well, stable, making that money. Why would I go and, go to become a nurse when I'm already making money? Right? And so that's another analogy to take a look at it. This compound, if the cation is stable, why would it want to go and become an alcohol or an ester or anything like that? It's cool where it's at, it's like, yeah. Yes. What time is it? Yes, we can take a quick break. So if you think about alkaline halides with the nucleophile, the rate is going to kind of be dependent on, we know the Sn2, right? So this is going to be the Sn2 contribution, and this is going to be the Sn1 contribution, right? So if we have a primary alkaline halide and methyl halides, all of those are going to only have the Sn2, so there's not going to be any contribution from the Sn1. Okay, secondary halides, that one's also only going to be Sn2, right? This reaction, the carbocatenation, is too slow that only that back-end reaction is going to happen fast, right? So it's so slowed and so delayed that your only contribution is going to be this because you don't have enough time to make this, right? It all goes into this part of the reaction. Okay, the ternary alkaline halide is only going to be Sn1 because they can't do that back-end. Right? Backside attack. So, and we know that that reaction is going to be slow, right? Because we know that that Sn1 part of it is going to be a slow reaction because you have to form the cation first. Okay, questions? Concerns? Okay, so earlier we talked about, let me clear this off. Last week we talked about that we could go through substitutions. So those are Sn reactions, right? Where we're just substituting one nucleophile for another nucleophile, right? And so in that case, we end up with just that substitution occurring. We can also get the elimination. We get an elimination, we end up with both nucleophiles detached from that hydrocarbon. Okay. And so in the case of an elimination reaction, all you're going to be doing is going to be removing that halogen from the carbon. And you're also going to be removing a hydrogen. Okay. So you're going to end up with your ion, and then you're going to end up with a hydrohalide. because you're removing that hydrogen, that adjacent hydrogen, you're going to be forming a new double bond. So you get the formation of a double bond. So in an elimination reaction, you're going to get a double bond forming, and then your both your nucleophile and your halogen are basically going to be removed. Your halogen is going to become an ion, and then that nucleophile that you're going to use is going to get the hydrogen added onto it. Okay. Okay. So here, this is an E1 reaction. So we're going to be adding a base to our alkaline halide. So as a result of that, we're going to end up with double bond forming. Here, we're going to end up with water, and we're going to end up with the bromine ion. Okay. So the halide gets freed. Our nucleophile then is going to remove the hydrogen from the adjacent. Okay. So the halide and the base are going to be in a transitional state. And so that's going to be our rate limiting step. And you guys remember what rate limiting step means again? Okay, here's the mechanism. Am I clear? Electrons are going to be transferred from that hydroxide to basically remove the proton. That proton is going to be freed, right? So then it's going to cause the electrons here to be moved to here to form that double bond, which then is going to cause these electrons to release the bromine. Okay, so you get your double bond forming on the backside where the hydrogen donated its electrons to, the hydroxide donates electrons to that hydrogen to remove that hydrogen from the methyl group. And so you guys are going to end up with 1 propylene, so 2 methyl, 1 propylene, propene, sorry, and water and bromide ion. Okay. The key is that the halogen that comes off, it's going to be freed, and it's going to always be the ion. So I have a question. So if we have bromine here, right? And let's say we had, instead of water, we had iodide. What would happen? Or would anything happen? What was that? I said, instead of water, we had iodide. What was that? Is that, would it be an acid? I'm saying that you're talking about, okay, yeah, so you're saying the hydrogen is going to be attached to this, okay? Yep. And will we get the same reaction? Yeah, but it would take longer, right? Why? Why would it take longer? What was that? That's not the reason why, but it's a poorer nucleophile than hydroxide. Hydroxide is a stronger base, so it's going to be more reactive, right? So that reaction is going to happen at a faster rate than in the case of the iodide, right? If I had chlorine there, would this reaction even take place? An even slower rate. If I had fluorine there, it would, right? Yeah. Not under these conditions, we would have to play with the solvent in that case, right? Okay. So B here represents base, it doesn't represent boron. Okay. So you have a base. The base is always going to be donating its electrons to the hydrogen to release that hydrogen. The hydrogen is then going to provide the bond, the electrons that were formed between the bond to the bond that is attached to that beta carbon, the other bond that's attached to the beta carbon. Then that's going to provide the electrons to release the bromine. So we're going to get the formation of our double bond. We're going to get our base attached to the hydrogen, and then we're going to get our bromine ion. Okay, so this process is called dehydrohalogenation. Dehydro because we're getting rid of that hydrogen, right? We're removing that hydrogen, dehalogenation. You're removing the hydrogen and you're removing that bromine, right? Okay. Now, the bromine is going to be coming off of the alpha carbon. The hydrogen is going to be coming off of the beta carbon. Okay, so they're not coming off the same carbon. Okay, so if we have regional selectivity or selective, so we have a beta carbon, right? Here's our bromine that's coming off. In this case, this is going to act as our alpha carbon, right? So we're going to be able to pull from the hydrogen off of this carbon and off of this carbon. So we're going to form both products, right? So we're going to end up with a 80% 2-butene, and then we're going to end up with 20% 1-butene. Okay, so 2-butene would be occurring here at the second carbon. So that's going to be the one that's going to be a little more favored. And then this one is going to be less favored. And then we're going to end up with 20% of that. Is there a reason that it favors? It has to do with that. Remember when we talked about that terminal, the end, double bonds at the end? They're not very stable, right? They're less stable. I mean, they occur, but they're less stable than if you have them in between carbons, right? Or more carbons, right? So they don't like being at the end. So these guys are less stable. So then that's right. That's why you get more abundance of this one, right? Okay. And so the major product is going to be the most stable alkene. This is less stable. We learned that when we were talking about the alkenes, when you get those double bonds at the end, they don't like so much, right? They like to be embedded. So, okay. And that's also, again, with this triple bond as well, too, right? They don't like necessarily being at the end. They like to be more central if they can. And why is that? Think about the resonance structures. I said, why is it that these guys are less stable? The double bonds at the terminal ends or at the very beginning of the hydrocarbon are less stable than putting a double bond, let's say, in between, two sets of carbons here. So conjunctive versus in a way, yeah. But if you think about its resonance structure, right? This guy's resonance structure has a lot more stability, a lot more stable possibilities, right? Where this one doesn't, right? So either I'm going to be shifting it over here, I'm going to be shifting it over there. Where these guys, I can shift it here, I can shift it over there, then I can also shift it beyond, right? Gives me more possibilities. So, and it leads to a more stable, their resonance structures are more stable than the resonance structures that would be for this guy. Okay. So if you guys take a brief look at, I think it's chapter 6. I think it was chapter 6. I'm old, so don't quote me. Okay. You're gonna ask a question? You guys good? Good? Okay. Okay, so this is just basically showing us, so the more stable the alkene, okay, so we know that 1-butene is less stable than the 2-butene, right? And so if we look at the Gibbs free energy, it gives us a lower energy product. And so again, it's more stable. We're gonna like that one more. And so as a result of that, we're gonna get more of this product for this product. Yeah, you'll get both products for them, but you're favoring the 2-butene. Like it. Oh, the sweatshirt, I'm sorry, just an aside. I'm working on the lack of sleep. I haven't had a lot of sleep this whole weekend. So my eyes are really heavy and my brain is not functioning completely. So random outbursts will happen once in a while. Okay. So if we have the alkene-like transitions, right? So if we take a look at this guy, so we get a partial positive here. This is where the hydrogen is going to be interacting. So that hydrogen is also going to try to form its bond with here. And then so we get secondary structure here. So this will be partial negative. So this guy is going to lead to our 2-butene, right? And again, we talked about those resonance structures. Well, this is going to lead to our 1-butene. This structure here is going to be less stable. Again, because we have all of these products that are going to be attached here, where the hydrogen is trying to bond to that carbon or be removed from that carbon. So, okay, so here's an example of another Sn2 reaction that kind of just looking at. I mean, sorry, an E2 reaction, not Sn2, an E2 reaction. So here, that's right. And why is it called an E2 reaction? And the 2 stands for what? 2-step, or it's going to be a binary. I mean, a bimolecular reaction. So it's going to be dependent on both products, the kinetics will. Yeah. Well, on both reactants. Sorry, not both products, both reactants. So, okay. So in this case, here's our hydrocarbon, and again, these are going to be our betas. These are betas. These are beta carbons here. And then this is going to be our alpha carbon. So a double bond is going to favor, again, being in that middle compared to being at the terminal end. Okay, so 30%, 70%. Okay, and then our product is going to be, so we're going to be plucking the hydrogen off, so we're going to get a product of an alcohol and then our bromide ion. So in the case of chlorine, again, these are going to be our betas, right? So our beta carbons. So these are going to be our beta hydrogens. So in this case, we're going to end up with a dye substitution. Okay, so and then in this case, we're going to end up with a mono substitution. So again, that double bond at the terminal end is going to be less stable than the one that's going to be more central. Questions? Concerns? Okay. Think about this one a little bit. Okay. So there are going to be limitations. So there's this Zaytif rule that basically leads to the more substituted alkenes. So if there's a conjunction, the more substituted alkene might not be the most stable. And so if that's the case, this guy we have a conjuncted double bond. So again, let's see, chlorine's here. So this is going to be our alpha. So these are our betas. Okay. So we'll have double bond forming here. And then that's the one. So double bond forming here. And so 1, 2, 3, third carbon. So, and then a double bond forming on 1, 2, 3, the fourth and the fifth carbon. Okay, so this one is a conjugate diene. And if we remember, the conjugated dienes are going to typically be more stable than the isolated dienes. And so our major products are going to be here. So conjugation, more substituted alkene may not be the more stable. Okay, so let me look back at this to get back to you guys on this one because I can't remember off the top of my head. So what time is it? 5:16. Okay, so we'll come back to this slide, and then I'm hoping it will start clicking here. So let's see. Access what the base. Okay, so in rule number 2, with the I'm gonna have to look up how to say the name too. The Zaytif rule, and this one kind of makes sense, right? So if we have a bulky base, the area that we're going to have the least access, that's going to give us the lower product, right? Because it's going to be harder to get in there. So the one that has the most access right? That's going to give us the greater product. Okay, so right here, we have a harder time getting into this area. That's going to be least. So this this beta carbon is going to be harder to get to than that N carbon, right? So as a result of that, we're going to have less product being made because again, it has to, okay, I'll fit in here, I'll try to fit in here. But again, the reaction is always going to be happening, right? You're going to have this reaction. So the products are going to be used up with that end product. So you're going to favor the end product where you have the double bond located here, 72%, compared to the product that you get here. Okay. And again, that's because the steric hindrance here makes it harder for the bulky base to kind of fit in there. If it was a smaller base, it would have no problems. But the fact that it's a bulky base, it has to get the right orientation just to be able to fit in. Okay. That and the other one, and I need to figure out why it favors the other one. So I have to go to my book. Yeah, so but it has something to do with that, the fact that we have the two double bonds, that we're forming two double bonds. And that plays a part in it. And I'll have to think about it a little bit, the reason why. So I'll have to get back to you on that. Okay, so as a result of that, we know that steric hindrance is going to play a huge part in how much of a product that we can end up with. So in the case of this reaction here, so depending on what our base is, that's going to have a factor, because the more bulkier that base gets, it's going to affect our product, right? So for instance, if we have a very simple base, such as this ethyl oxide, and we're going to have the more stable product is going to be favored. And then stable product favored, but we're still going to get some of the less product, right? Like we saw earlier. As the base gets bulkier, a much bulkier, so now we have a ternary oxide, or ternary oxide. Then in that case, we're going to have the less stable alkene being favored, because it's not able to get into the more favorable position. Okay. And that's the same thing here. We're getting even bulkier in the sense that now this chain is getting even larger, and the numbers they drop even more, right? And then as we get even bulkier, both sides are getting longer. Now we're dropping down to 8% and 92%. So you could just imagine if we had one that was even longer than this, the effect it would have. So we have to pay attention to that concept of steric hindrance, right? And so those branching structures, those substitutants, play a huge part. The more substitutants you are, the more and the longer those substitutants, those chains are, it's going to limit the accessibility to certain points in terms of the reaction. Okay. Does that make sense? Yeah, no? Give or take? Okay. So we already know that alkaline fluorides form a less stable, we know that they are less likely to react. They don't like reacting in the first place. They like to stick on there, right? So, but these guys are going to form a less stable alkene. So if we take a look, we look at our alpha carbons. So this is our alpha carbon. These are our betas. And so we get less formation with a stable beta than compared with the unstable beta. So fluorine just kind of throws everything out of the hamper entirely. And it doesn't really matter if it's a bulky base or if it's a tiny base. It just favors the less stable product. So that kind of helps us, because if we want to tailor a reaction to favor that less stable product, then we know that we can use fluorine to do it, or we can use bulky bases to do it, right? Okay, so in this case, you're going to have a transition state that's going to be a carbonation. So it's going to be a carbon anion in the case of fluorine. So this guy's going to be partially negative. This guy's also going to be partially negative. Okay, so that's the same thing that's happening here. The more stable state, is going to be, in this situation, it's going to be this guy, the terminal one, compared to what we have here. This guy's going to be, this transitional state is going to lead to 2-pentene, which is going to end up being less stable than the 1-pentene. And it's because now these guys are going to act like the carbon is now going to act as if it's negatively charged, kind of like what we would have in the case of the halogen earlier. Okay, so yeah. Yep. Okay. So you guys already see the trend, right? So when we have the cation being surrounded by more bulkier things causes it to be more stable. And then, so if we go from a tertiary carbocation to a secondary carbocation, so more stable to least stable. So the methyl cation is the least stable. Now, this is just the opposite in the case of the anion. This is going to be less stable and is going to be more stable with the methyl. Okay. So let's go back and see that pieces together. So we know that in this case, this guy is going to be more like a methyl carbocation, which is going to be more stable than this guy, which is going to be like a secondary, right? Carbocation. Okay. Okay. So in the case of the products that are going to be obtained here, so if X is going to be iodide, then we're going to get the more stable product is going to be higher. As we get bigger, as we get smaller, bromine is smaller than iodine, we're going to get a little less of our stable product. As we get to chlorine, which is even smaller than bromine, we're going to get a little bit less than our more stable product. And then we're going to get a huge shift when we get to fluorine, right? And we know that that has to do with its electronegativity. So we want to definitely pay attention to which halide we're using for this process. Okay, I think I'm going to go ahead and stop on this slide before we get to E. Actually, let's go ahead and finish this slide. Then we'll stop at reaction because we'll start talking about more reactions. Okay, so if we look at the relative reactivity of the alkaline halides of the E2 reaction, so we have the tertiary alkaline halide is going to be more reactive than the secondary alkaline halide, which is going to be more reactive than the primary alkaline halide. Sorry. So in the case of the E2, we know that this guy is going to be like the closer you are towards the end, right? Or sorry, the closer you are towards the end, the worse your reaction is going to be, right? Because then in this case, you're going to have it on that terminal end. And so that's going to be less stable than if we put it more central, right? And then in the case of this ternary, we actually have a lot of possibilities. We could put it this side or that side, which, allows for even more stability than the other two. So we have, in this case, 3 alkaline substitutions, right? So you'll have your R here, your R here, and your R here. In this case, you only have 2 alkaline substitutions. And then in this case, we only have 1 alkaline substitution because we're at the terminal end. This guy is always going to be less stable. This guy is going to be more stable. This guy is going to be the most stable, right? Okay. So that tertiary is going to give us a more stable product. Okay.